Good morning, everyone. I would like to introduce to you today my new teaching assistant, Ronan. Since I can't be on campus, I needed somebody at home to help me out. So Ronan's going to be along for the semester, answering your questions on Folio if I can't get to them about course content.
I don't even know about anything.
What? What good are ya? I'm just kidding. I'm so glad you're along for the ride. And Ronan won't really be answering your questions on Folio. That's still on me. But I will give 5 bonus points to the first person on Folio who posts a question for Ronan to answer. It doesn't have to be about stats, just to make sure that somebody's watching these stinking videos. Otherwise, why am I taking the time? Alright, thanks, buddy. Love you.
Love you.
Alright, guys, so I'm going to get down in the corner here so that we are focusing more on the content. But this screencast today is to help give you a little bit more context if you're not able to be with us in a synchronous environment, so that you can kind of keep up with what we're doing. In ANOVA, we have a number of different learning objectives that we want to accomplish. Hopefully by the end you should be able to define the one-way between subjects ANOVA and talk about each source of variation that happens with this statistical analysis, calculate the degrees of freedom for a one-way between subjects ANOVA and locate the critical values, identify the assumptions of this test, and compute the and interpret the results in SPSS, both for the test itself and any post hoc testing that we'd need to do, and then be able to write that up in APA format. So, the key thing about ANOVA is that we're moving beyond 2 groups. If we have 2 groups or 2 levels of our independent variable, and we want to compare them on some kind of outcome or dependent variable, we really cannot sometimes tell about what might be happening in between. We can't tell about anything beyond those 2 groups, and we can't talk about anything in between those 2 groups. So a t-test is nice, but it's fairly simple. It does not allow us to extrapolate to what might be happening to other groups outside, and it doesn't help us interpolate. Maybe we've taken an independent variable and cut it into 2 chunks, but it was really something that was continuous data where we might be better to see 3 groups, 4 groups, 5 groups or levels. And so sometimes we need an ANOVA to help us do more complex or interesting questions to test more than just 2 groups or 2 levels of the independent variable and how those affect the dependent variable. So, for example, if we wanted to run a study with 3 levels of an independent variable or 3 testing groups, maybe we could look at gum type, with no gum being our control group, fruity gum and peppermint gum being our 2 levels of our independent variable. Or maybe we wanted to see how students' grade point averages compared across people's class standing, and we might have 4 groups, freshmen, sophomores, juniors, and seniors. This is the kind of test, then, that we would be able to do with an ANOVA. So, let me get back to the place where I can actually flip my slides again, because it's not doing that for me. Ah, stink. Okay, I think I got it going. So if we're looking at 3 groups, we want to know where the differences between those groups might be. And now, there we go. In our gum example, we want to know if one group is different from the other, or if they are not equal. But it might be that all of the groups are different from each other. A is not equal to B, B is not equal to C, and A is not equal to C. Or it might just be that these 2 groups are equal and these are the only ones that differ. Or, if we were looking at our other example with class here, and how that might affect grade point average, maybe there is a way that freshmen are doing better than seniors, who are doing better than sophomores, who are the same as juniors. Or we might find all kinds of differences within those groups. So one thing that you're thinking is, well, if I can do a t-test with 2 groups, why don't I just do a t-test for this pair, and a t-test for that pair, and a t-test for that pair? Well, that would kind of work, but it's got problems, and so doing multiple t-tests is not ideal instead of doing an ANOVA. What happens is if we conduct multiple t-tests, it inflates our probability of a type 1 error. You might remember from hypothesis testing that a type 1 error means that the likelihood or possibility that we said there was a difference when in the real world there wasn't, because we found something that kind of stuck out in the tails of our distributions as unusual. And so statistically we said that looks important, but maybe it really was just a fluke. And so every time we do a comparison, we have that risk of type 1 error based on how we set our alpha level. So if we set our alpha level at 0.05, we're going to be wrong in our decision 5% of the time. Well, then multiply that by the number of times you make comparisons, and we might be making a whole lot of mistakes. One way that we could figure out the likelihood, the probability of making a type 1 error, is take 1 minus the alpha level for however many comparisons we're doing. So again, here m is the number of comparisons, alpha is our alpha level for each comparison, and if we did this filled out this formula for a lot of groups, our risk of making a type 1 error or saying that something is important when it's not goes up tremendously. And this is simply too much risk. So an ANOVA helps us make one comparison looking across all the different pairs that we want to compare all at one time. So that helps keep our alpha level, our probability of making a type 1 error fairly low. Alright, so an ANOVA is an analysis of variance. It analyzes the variance in a set of scores. And remember that our goal with ANOVA, like it was in t-tests or z-tests, is to determine the difference in scores across groups and to see if that's greater than the differences overall. So ANOVA is one of those ones that looks for differences in levels of the groups. It's not a statistic that's looking for relationships between variables. That's what correlation and regression and chi-square are for. So if we had 3 different drug doses, we could look at some kind of outcome score for people who didn't get any drug, got a little bit of the drug, got a lot of the drug. We could see if people's outcomes differ across those 3 groups. Right? So we would average these folks all together to get a grand total, but we're looking to see if the differences in their outcome are different across those groups. Alright, so when we conduct research, we are setting out hypotheses where we know or hope that people are going to score differently. We set our research hypothesis looking for differences, not for no differences. Why would we spend time and money looking for no differences? And we know that people are going to vary individually in how they respond to a medication or a treatment. So we want to know if our treatment causes people to score differently from each other than they would if they'd have just not gotten any treatment at all. Alright, so ANOVA compares differences in scores between groups, maybe treatment versus no treatment, and this is also known as our between group variability. And we're also going to compare that to what we naturally know, how people are going to differ, because not everyone's the same. So we're trying to see if the differences across the groups is more distinct than the differences we see for people across the board. The second piece is known as the within group variability. So there are actually 2 pieces of variability that we have in ANOVA. We have the mean squares between, or the differences for people within the group, and we divide that by the differences within, that natural variability. So another way we could look at that is the difference in group values is more distinct than people's natural variability from each other, regardless of groups. You could also mathematically look at it as the difference in group means, or the variability across group means divided by the differences across people as a whole. Alright, so with ANOVA we can do more than 2 groups. We don't just have to have yes or no, black or white, all or nothing. We can look at multiple groups at the same time. So remember that when we talk about factors in ANOVA, a factor is how many independent variables we have. A level is the number of conditions across that factor. So if we were doing our gum example, we had 1 factor with 3 levels. If we were looking at our class year example, we had 1 factor with 4 levels. Right? Class, 4 conditions. Here's our factor over here on this side, and here's the levels over here. So we're going to compare our group mean for each group and see how they score, and compare that by the grand mean and see if any of these groups are different from each other. Alright, some key things about F values. First off, the F distribution differs from Z and T distributions that we've been doing before in some pretty key ways. First off, our F value is always positive. It cannot be negative. In z-test and t-test, you can get a negative value, and that means those folks are below average. With an f-test, we're always going to get a positive value, because an f is centered around 1, not 0. The other thing about an F distribution is it's skewed. It's not normal or symmetric. We're used to, with t-tests and z-tests, looking at two sets of tails so we can tell if something is above average or below average. With an F value, since it starts at 1 and can't be negative or below that, we're only looking at a one-tailed distribution. So our assumptions for an ANOVA test, where we use an F statistic, is that still we have a normal sampling distribution. Either we have a normally distributed dependent variable, or a whole lot of people that will kind of be able to, the statistic can tolerate if it's a little bit skewed or wonky. That we have homogeneity of variance, that each of those groups has similar patterns or descriptions of data. So this group shape looks like this group shape, looks like this group shape. And that we have independent observations for this ANOVA, that we're not having a within subjects design where people are repeating things. We are looking at independent groups for levels of our independent variable. Our hypotheses, and we'll kind of wrap up here before I get into the stats video that shows you how to run an ANOVA. If we're talking about what we're testing, remember that our hypothesis, our null hypothesis, is that things are the same. So the mean of the first group is going to be equal to the mean of the second group, however many groups you have. So mathematically out to k, the number of groups that we have available, whether this is 3 or 17 or 2,694, that we're assuming that those groups' means on the dependent variable are always going to be equal. And our alternative or research hypothesis is that we've got something unequal. Now, we don't know where those differences are. We'll talk about post hoc tests in another presentation, but we're assuming that there is a difference, something unequal, somewhere. So keep in mind, we're always looking for an F statistic that is greater than 1. It can't be 0, so F tests are one-tailed. So we're not going to have to worry about whether we're setting up a one- or two-tailed test here. It's always going to be one-tailed, that something's different. All right, so a couple quick examples before we flip over to stats. Here's an example of how you would set up step 1 of hypothesis testing. If we started out with a research study where we were thinking the amount of study time varies by class level. I'm not sure from your perspective who you think studies the most, but you might realize that freshmen, sophomores, juniors, and seniors might differ on how much time they're putting in on studying. Maybe you think it gets more as people go higher in school, or maybe you're realizing that seniors have other things to do, so maybe sophomores and juniors are going to study more than freshmen and seniors. Again, the hypothesis we set up is that there's going to be a difference somewhere, and the null hypothesis suggests that study time does not vary by class level, that those means are going to be equal. So keep in mind in setting up your statistic to run that we need to describe our hypotheses both in stats notation or math, and in some kind of sentence or English, so that we're helping for you to show me what you know we're testing mathematically, and you know how to describe that to somebody. Here's a second example. If we were looking at therapy and whether that helps depression, we could look at 3 different kinds of therapy treatment and see if they are different in battling depression, or whether they are the same. So here's a second example of how to set up those null and research hypotheses. All right, we're going to pause here.